Okay, hello everyone. Let's move on to chapter 10, which is hypothesis testing. In the hypothesis testing, the objective of statistics is to make inference about unknown population parameters, and these inferences are phrased in one of two ways: as estimates of the respective parameters or as tests of hypotheses about their values. And in previous chapters, in chapter 8 and 9, we learned about how to estimate respective parameters. And so in this chapter, in chapter 10, we were going to learn how to test hypotheses. Okay, so this is a short introduction for hypothesis testing. Let's move on to chapter 10.2. It's elements of statistical test. For the elements of the statistical test, there are four main important things. The first one is null hypothesis. Second one is alternative hypothesis. Third one is test statistic, and fourth one is rejection region. And probably you guys may learned a bit about hypothesis testing in elementary classes in statistics. So let's review some these concepts. So the null hypothesis reflects no difference, no association, or no effect. And the alternative hypothesis, we will call it HA, it reflects the investigator's belief. So in most of research, we make a hypothesis about our belief, and we want to reject the null hypothesis so that we can support our belief. That's the user story, but sometimes we reject HA. Sometimes we reject H0, sometimes not. Anyway, this is how the statistical test goes. And the test statistic is a function of the sample measurement on which the statistical decision will be made. So in hypothesis testing, we use this test statistic and to decide whether we will reject the null or not, we use the decision rule, like rejection region. This rejection region specifies the values of the test statistic for which the null hypothesis is to be rejected. So we use distributional assumption and make a rejection region based on that distribution. So let's go more details from the following slide. Okay, let's move on to a simple example. Suppose that 15 voters are randomly selected from the city, and Y, the number of favoring Jones, is recorded. So the Y, the number of favoring Jones, this is actually sum of Bernoulli trials. And Bernoulli trials, either 0 or 1, with probability P. And if none in the sample favor Jones, if Y is 0, what would you conclude about Jones' claim? Let's say that Jones' claim is that less than 50% of people favor Jones. Let's say that this is Jones' claim. So the investigator's belief goes to the alternative hypothesis. And if we don't know nothing, probably we would assume that P equals 0.5, just like balanced coin. So our null hypothesis is P is 0.5, and our alternative hypothesis is our investigator's belief that which is Jones' claim. And for this class, the test statistic is Y, the sum of Bernoulli trials, and that is 0. And actually, the sum of Bernoulli trials follows binomial distribution with n p. And so under the assumption, under the null hypothesis, under the P equals 0.5, we can calculate the distribution about sum of bi, which is y, and we can calculate the probability distribution of y, and we can calculate that the test statistic, uh, the probability of y equals 0 under and when y is following binomial distribution 15 and zero point 0.5, and actually this probability would be very small, and so the under this null assumption, the probability of observing this test statistic under the null hypothesis, the probability of observing y equals 0, it would be very small. So probably we would reject the null hypothesis. We would reject H0, and we will accept the alternative hypothesis, which is less than 50% of person favoring Jones. And with this distributional assumption, we can calculate the rejection region. And in here, actually, we need to decide the level of the probability. So maybe we will call it alpha. If you set alpha equals 0.05, then the probability of this region is about 0.05. That's how you calculate rejection region. And so this is a small example to let you understand the concept that I explained in the previous slide. And let's move on. There are two types of errors in statistical testing. We call it type 1 error and type 2 error. If H0 is true, but we can reject H0, this is the probability of this situation is type 1 error. And if the reality is H0 is false, but we do not reject H0, this is also possible, and the probability of this situation is called type 2 error. So we can write it as this way from the textbook. A type 1 error is made if H0 is rejected when H0 is true. And in mathematically, we can write it this way. The probability of rejecting the null hypothesis given the null hypothesis is true. This is type 1 error. And about what is the type 2 error? A type 2 error is made if H0 is accepted when alternative HA is true. The probability of a type 2 error is denoted as beta. Yeah, we call type 1 error as alpha, and we call type 2 error as beta. And the beta is probability of do not reject H0 given H0 is false. Okay, so this is concept of type 1 error and type 2 error. And actually there's one more thing. We call power. The statistical power of test as 1 minus beta. This is another definition. And so this power implies that the probability of effectiveness of the test. If we have large amount of power, then if the H0 is false, the probability of reject the null is higher. So we want to have a test with large power because most of times we want to reject the null hypothesis. Okay, let's move on to example 10.1. For Jones political poll, n equals 15 voters were sampled. We wish to test the null hypothesis H0 is p equals 0.5, and again the alternative hypothesis is p is less than 0.5. The test statistic is y, the number of sampled voters favoring Jones. Calculate alpha if we select rejection region as this. Okay, so from the definition of alpha, the type 1 error rate, this is probability of reject H0 given H0 is true. So this is alpha, and the alpha H0 is P equals 0.5, and rejecting H0 is the set Y is less than 2. So we want to calculate the probability of Y is less than equal to 2. And we know that under the null hypothesis, under H0, Y follows binomial distribution with n equals 15, p equals 0.5. And so, using this binomial distribution, we can calculate the probability of y is less than equal to 2. And to calculate this number, actually we can use R. So to calculate this sum of binomial distribution, we can use p binom function in R. And here p binom is a function in R, and this is cumulative sum of binomial distribution. This part is n equals 15. This part is p, probability is 0.5, and this 2 is this one. So we can calculate the level alpha. This is alpha, and it's about 0.00369 something. Okay. Let's move on to example 10.2. Refer to example 10.1. Is our test equally good in protecting us from concluding that Jones is winner if in fact he will lose? Suppose that he will receive 30% of the votes. What is the probability beta that the sample will erroneously lead us to conclude that H0 is true, and that Jones is going to win? Okay, so we want to calculate the beta. And actually, the situation is like this. H0 is P is 0.5, and the alternative hypothesis is P is less than 0.5. And assume that we received 30% of the vote. And if the truth is this situation, P is 0.3. If the truth is this situation, and what would be the probability that we will erroneously do not reject the H0? So this is truth, so we should reject H0. But what would be the probability that do not reject H0 given HA is true, and actually this is P equals 0.3. P equals 0.3. So this is type 2 error, beta. And actually, again, the rejection region, we will use the same rejection region. So not rejecting H0 is the complement of y is less than or equal to 2, complement set. So this is y is greater than 2. Okay, and here we know that y follows binomial distribution with n equals 15 and p equals this time 0.3, and we want to calculate the probability of y is greater than or equal to 3, and actually this is 1 minus p y is less than equal to 2, and actually we can calculate it using R, which is 1 minus p binomial 2, 15, p is 0.3, and we can calculate this as our beta. And actually we can see the high error rate of beta. So we want to minimize both type 1 error rate and type 2 error rate. But for this case, type 2 error rate is quite large. So most of times, even if the truth is p is 0.3, probably we cannot reject the null hypothesis most of times because the beta is about 0.87. When this kind of things happening, we need to increase the sample size so that we can have lower type 2 error rate. And also, sometimes we talk about beta, and sometimes we talk about power, which is 1 minus beta power. Statistical power, it is 1 minus beta, and we would like to increase the statistical power, the power to detect something, power that is rejecting H0, probability of rejecting H0, that's 1 minus beta, and so we want to minimize, we want to have lower alpha, lower beta. We want to have lower type 1 error rate and type 2 error rate, and we want to have larger power, power to detect something new. That is the power to detect, power to probability of rejecting H0 if alternative hypothesis is true. That's the power. Okay. Let's move on to example 10.3. Refer to example 10.1 and 10.2. Calculate the value of beta if Jones will receive only 10% of the votes. Okay, so this time we will have our alternative situation as p equals 0.1. If the truth is p is 0.1, what would be the probability of rejecting the null hypothesis? So we want to calculate beta, which is probability of rejecting H0 given the truth is p is 0.1. And here again, this is y is rejecting the null is y is greater than 2. And actually this is 1 minus probability of y is less than or equal to 2. And here y follows binomial distribution, n is 15, and this time p is 0.1. And so we can calculate it using r again. So this time p binomial n equals 2 and n equals 15 and p equals 0.1. And from here, our beta is this time 0.18. So we can see that lower number of beta. So if the truth is about 0.1, then we can conclude that this time we can have lower beta, lower type 2 error rate. So if we have large amount of distance, so the P0, which is 0.5, and if we have the alternative P is larger distance, then we can have larger power, small amount of type 2 error rate. So and the other way to increase power or decrease the error rate is increasing the sample size n. So this time our n is only 15, and so to decrease the type 1 error rate and type 2 error rate, usually we fix the type 1 error rate alpha. Usually we fix the type 1 error rate alpha and see the beta, and so to decrease the type 2 error rate beta, we should increase the number of observations. Okay. Okay, now let's move on to example 10.4. Refer to the test discussed in example 10.1. Now assume that rejection region assume that we have larger rejection region. Calculate the level alpha of the test and calculate beta if p is 0.3. So if we have larger rejection region, probably we will have a larger type 1 error rate alpha. So the alpha is the probability of rejecting H0 given H0 is true. And so the rejection region is y is less than or equal to 5 given the null thing. So in this case, p is 0.5. This is the null situation. And so in this case, y follows binomial distribution and it's 15, p is 0.5. And the other question to solve is calculate beta, and beta is by definition probability of do not reject null given alternative is true, and in here assuming p is 0.3. And so in this case, y will follow binomial distribution 15 and 0.3. And from this information, you can use R to calculate the probability of these things. And here, do not reject is actually probability of y is greater than y. So using p-norm, the probability of y is less than equal to 5 given p is 0.5, that is p binomial 5. This 5 is from here, n is 15, and p is 0.5. And also for beta, we are calculating y is greater than 5, so it is actually 1 minus probability of y is less than equal to 5. And so it is 1 minus p binomial, 5 is here, and we have 15 observations, and the probability, this case, is 0.3. So we can calculate our alpha is 0.15, and our beta is 0.278. This is our alpha, and this is our beta. Okay. We have one homework for chapter 10.2. Let's move on to chapter 10.3, common large sample test. Suppose that we want to test a hypothesis concerning a parameter theta based on random sample of y1 to yn. An estimator theta hat has approximately normal sampling distribution when with mean theta and standard error sigma theta square. And for some common things, they are listed in table 8.1. So the common parameters for theta, they are mu, p, mu1 minus mu2, p1 minus p2. They are very common parameters, and also we can use point estimator of these, and the standard error estimator for this one. These are these, and with large n, we know that these point estimators follow normal distribution by using CLT, central limit theorem, and so usually we use that assumption when we are testing, when we are doing hypothesis testing about these parameters. Okay. So here's an example. Let's say the null hypothesis is theta is theta 0, and the alternative hypothesis is theta is greater than theta 0. And let's say our test statistic is theta hat. These are these, and the rejection region would be the theta hat is greater than k. This time, alternative hypothesis is theta is greater than theta 0. So we want the alternative hypothesis is that theta is greater than theta 0. And so if our observation is very large, then it it would more favoring the alternative hypothesis. So the rejection region is this side. And to decide the rejection region, again, as we learned from the previous chapter, we consider type 1 error rate and type 2 error rate. Here it describes alpha, type 1 error rate, the probability of rejection region under the null hypothesis, that's type 1 error rate, and so the area here is alpha. So the area here is probability of a rejection region given H0 is true. So given H0 is true, the distribution is like this. Large sample rejection region for H0 versus H alpha. Okay, let's move on. If we desire alpha level test, what this means is that we want to have probability of rejecting given H0 is alpha. And actually that is this situation. The probability of our this one follows the standard normal distribution by using CLT, and so probability of theta hat minus theta 0 divided by sigma theta hat is larger than Z alpha is alpha, and so we want to rewrite this one, and that is this thing, that theta hat is greater than this value, and actually this value is k. So if we write this value as k, then the probability would be alpha. So if we desire alpha level test, we will set k as this one, and then we will get alpha level test. So when we are doing tests about this situation, the test statistic is theta hat minus theta 0 divided by sigma theta hat, the standard error of theta hat, and the rejection region can be calculated as Z is greater than Z alpha. So this is how we derive the alpha level test for large sample, for common large sample test situation. And for different hypotheses, we can calculate different rejection regions. So we covered this situation when theta is greater than theta 0. In this situation, we derive this one, and similarly, we can think about other situations when theta 0 is when theta is less than theta 0, and also when theta is not equal to theta 0. And so here in this situation, it is the rejection region can be written as this way, minus Z alpha, which is this one, and then the rejection region is theta hat is less than theta 0 minus Z alpha sigma theta hat. And also for two-tailed test case, the two-sided case, the situation is either this one or this one, and so the rejection region would be derived as this thing. Okay. Here it describes general steps for the hypothesis testing. So for the step 1, set up hypothesis and determine the level of significance. So at this stage, we define the statistical hypothesis and decide the level alpha. And the second step is select the appropriate test statistic. So here for the large sample test, the approximate test statistic is this thing. Z is zeta n minus zeta 0 divided by standard error of zeta hat, and usually this one can be from that table 8.1. For one sample population parameter, usually you will get the pointer estimate y bar. And so if we take y bar, then y bar minus mu 0 divided by standard error of zeta hat, which is sigma over square root of n, and actually for the larger sample size you will set sigma estimate, put sigma estimate here and approximate it using normal. And so by using these point estimators and standard error estimate, you can easily derive hypothesis testing for target parameter mu, p, mu1 minus mu2, p1 minus p2. And okay, so that's the test statistic. And step 3 is set up the decision rule. And decision rule is one of these situations. Depending on your hypothesis, alternative hypothesis, you can set up decision rule. And the first step is compute the test statistic. So first step is computing values. So you decide test statistic and rejection region. So in step 4, you calculate exact value of that. And step 5 is concluding your decision, like rejecting the null hypothesis or do not rejecting the null hypothesis, something like that. So this is general steps for the hypothesis testing. So when you are solving your problem, check this slide and try to solve the problem. Then I think it would not be very difficult, but yeah. Anyway, let's move on. Let's move on to example 10.5. A vice president in charge of sales for a large corporation claims that salespersons are averaging no more than 15 sales contacts per week. He would like to increase this figure. As a check on his claim, n equals 36, salespeople are selected at random, and the number of contacts made by each is recorded for a single randomly selected week. The mean and variance of 36 measurements were 17 and 9, respectively, and does the evidence contradict the vice president's claim? Use a test with level alpha equals 0.05. So the vice president want to do the test whether salesperson are averaging no more than 15 sales or not. So our hypothesis is something like this. So our H0 would be mu equals 15 versus the alternative hypothesis is mu is greater than 15. This is something that we want to like to test, and the alpha is 0.05. So this is our hypothesis. And step 2, select the appropriate test statistic. For testing the mean, the user test statistic is y bar, and by using y bar minus mu 0 divided by standard error of y bar, this follows the normal distribution with mean mu and mean 0 and variance 1, standard normal. And in here, the sigma y bar, this is sigma over square root n. Okay, And let's move on to step 3. Set up the decision rule. And the decision rule, if we set up this as z, decision rule is z is greater than z alpha. This would be our decision rule. And this z alpha can be calculated using r like this. And so decision rule is z is greater than or equal to z alpha, which is 1.64, about 1.64. This is our decision rule. And step 4 is compute the test statistic, which is G. And our test statistics G is Y bar, and Y bar is 17, the mean 17 minus mu 0, which is 15, and the variance is 9. So our standard error estimate is 3 over square root of n, and we have 36 observations. So this is 3 over square root of 36, and this is 6, 2 times 2. This is 4. And so the test statistic is 4, and this 4 is greater than or equal to 1.64. So we reject the null hypothesis. So in step 5, we reject H0, null hypothesis. Okay, let's move on to example 10.6. A machine in a factory must be repaired if it produces more than 10% defectives among the large lot of items that it produces in a day. A random sample of 100 items from the day's production contains 15 defectives, and the supervisor says that the machine must be repaired. Does the sample evidence support his decision? Use a test with level 0.01. Okay, so first, let's set up the hypothesis and level of significance. And supervisor the factory must be repaired if production is more than 10%, and supervisor says that we should repair. So hypothesis is that H0 is P is 0.1, and H1, HA is P is greater than 0.1. So the error rate is over 0.1, so it should be repaired, and we want to test this with alpha level with 0.01. And what would be the step 2? Select the appropriate test statistic. And this time we are inferencing about the proportion. And for the proportion, minus P0 divided by square root of, and actually sigma P hat. This would follow normal distribution with mean 0 and standard deviation 1. And in here, sigma P hat is square root of P1 minus P divided by n. And here, actually, the test statistic is derived based on the null situation. So what we are doing, we are calculating the probability. We are doing inference given the null situation. So we should put P0 here, which is 0.1 when we are calculating this one. Okay, and this is our test statistic, and let's set up the decision rule. And the decision rule is z is greater than small z level alpha, which is 0.01, and this is actually z is greater than 2.33, about 2.33. This number calculated from here, and uh, and the last step, step 4, is computing the test statistic. So p hat is 0.15 minus p0 is 0.1, and divide by square root of zero point 0.1 times 0.9 divide by n. N is 100. And if you calculate this number, this one becomes 5 over 3, and which is 1.66, about 1.667. And is this one greater than 2.33? No. So 1.667 is not greater than 2.33, so we reject the null hypothesis. So we reject, do not reject the null hypothesis. So do not reject. H0. And from here, if we cannot reject the null, then does it means that supervisor is wrong? So supervisor said that the error rate may be over 0.1, but actually from the statistical test, we cannot reject the null hypothesis in this situation. And actually, we cannot tell that supervisor is wrong. And from at this point, the alpha level is very small. So this 1.667, it's quite large, but with level alpha level 0.01, currently it do not reject the null situation, but probably with alpha level 0.05, it should be similar to 1.66, and so what we can say is that we do not reject the null situation, and we cannot tell that the supervisor is wrong or right. We just say that with alpha level 0.01, we cannot reject the null hypothesis. So this is our conclusion for the problem. Okay, let's move on to example 10.7. A psychological study was conducted to compare the reaction times of men and women to a stimulus. Independent random sample of 50 men and 50 women were employed in the experiment. The results are shown in table 10.2. Do the data present sufficient evidence to suggest a difference between the true mean reaction times for men and women? Use alpha equals 0.05. And so at this time, this is two-sided test. So for the hypothesis, it is testing whether man and woman difference. So the test hypothesis is mu1 minus mu2 is 0 or not 0. HA alternative hypothesis is mu1 minus mu2 is not 0. And actually, we can also write it as mu1 is equals mu2. This is same as mu1 is not equal to mu2. Okay, and so this is our hypothesis, and our alpha is 0.05. And in step 2, we select the appropriate test statistic. For mean difference, the test statistic is y1 bar minus y2 bar and minus mu1 minus mu2 divide by sigma y1 minus y2. This will follow normal distribution, standard normal distribution, and from here the standard error of y1 bar minus y2 bar is square root of sigma 1 square over n 1 plus sigma 2 square over n2. Okay, so oh yeah, okay, and we have estimate for sigma 1 square and sigma square 2 here. Okay, and what's next? The next thing is set up the decision rule. The decision rule for two-sided test is the absolute value of z is greater than z small z alpha over 2, and so this one is absolute value of z is greater than z alpha over 2 can be calculated using R. It's about 1.96, and so this is our rejection rule. And the next thing is compute the test statistic. So y1 bar minus y2 bar, which is 3.6 minus 3.8, 3.6 minus 3.8 divide by and mu1 minus mu2 under the h0, it is 0, so this part is 0, and divide by sigma y1 bar minus y2 bar, which is square root of sigma 1 square, which is 0.18, 0.18 divided by 50 plus 0.14, 0.14 divided by 50. And after you calculating this using calculator, you will get about 2.5 and minus 2.5, and this absolute value of minus 2.5 is greater than 1.96. So you reject the null hypothesis. So reject null hypothesis, and you can conclude that the man and woman have different stimulus effect. The reaction time of man and woman is different with alpha level 0.05. So this is our conclusion, and yeah, that's it. Homework for chapter 10.3 are these.